Okay, this will be chapter 10C, I believe, for the hypertension, atherosclerosis, and heart disease from the book Medical Reformation by Peter Rogers. Okay, this slide right here shows a more detailed look at the plasma membrane of a cell. We're especially sort of emphasizing nerve cells here because I originally made the slide in the context of talking about the brain, but it's the same overall situation for other cells. So basically, the concentration of sodium is about 10 times higher in the extracellular matrix than it is inside the cell. In the cell cytoplasm, it's about 14. In the extracellular matrix, about 140. So that's 10 times higher out there. So what that means is there's a chemical concentration gradient of sodium, and it energetically wants to come into the cell. There's also a charge gradient, an electrical gradient of negative 65 millivolts across this plasma membrane. So a sodium ion outside the cell very much wants to come in, not only because it's a positive charge attracted to the negative charge inside the cell, but also to equilibrate its concentration gradient. And the energy of sodium wanting to come into the cell is coupled to pumping calcium out of the cell. This is the NACA exchanger, sodium-potassium exchanger, often abbreviated NCX. And other thing can be done with this coupling. You can couple sodium's entry into bringing amino acids into the cell. You can couple sodium's entry into the cell to pumping protons, acid out of the cell. So this just goes to show you how powerful this electrochemical gradient is for the cell, enabling it to get work done. Okay? When calcium gets high inside the cell does whatever that cell is designed to primarily do. If it's a smooth muscle cell, it'll contract. Vascular smooth muscle cell will contract and narrow the artery. If it's a brain cell, it'll release its neurotransmitter into the synaptic cleft, which then diffuses to the postsynaptic neuron and exerts an effect upon it. Okay? Okay, it's just a little more detail about the concentration of ions. We talked about sodium in the blood or in the extracellular matrix being about 140 inside the cell, 10 times less. It's really just about the exact opposite with potassium. So it's essentially tenfold difference, but this time the higher amount is inside the cell, the potassium. Okay, with calcium, it's 10,000 to 15,000 times higher in the extracellular matrix than it is inside the cell. Excuse me, and the significance is you always need ATP to pump against this gradient. So that's why it takes a lot of energy, and that's why you need intact functional mitochondria if you're going to be able to effectively pump all that calcium out of the cell. Cells in the plasma membrane have the NCX, the sodium calcium exchanger, that's super fast. Okay, it can pump about 5,000 calcium ions per second. And you also have a plasma membrane calcium ATPase, and that's relatively slow, about 150 molecules of calcium per second. So cells that are excitable, like neurons, skeletal muscle cells, they will have a significant amount of this NCX fast pump. A regular cell might primarily just run with the plasma membrane calcium ATPase. Okay. Okay, we talked about the concentration gradients. Oh, the ATP use directly by the potassium sodium ATP pump, potassium sodium ATP pump here, abbreviated KNA for potassium sodium ATPase. That's called primary active transport. And then the fact that the gradient for the NACA exchanger is coupled to it, that's called secondary active transport. So primary active transport and secondary active transport. Okay, here's a slide from the work of Peter Quo. He was a cardiologist in Pennsylvania in the 1950s, and he fed his cardiac angina patients a high-fat meal with saturated fat. And then he drew their blood, he drew their blood every 30 minutes. And what he noticed was it was at the time of peak lipemia that the patients were most likely to develop angina. And so this was related also in the 1950s to everybody learning about saturated fat being bad for you in terms of being atherogenic. And so he further confirmed that. Okay, when the highest amounts of saturated fat are present in the blood, you get the most anginal episodes. So he took a whole bunch of patients with known coronary angina, meaning symptomatic chest pain associated, for example, with exertion, and he fed them these high-fat meals. What was interesting was in the 1960s, these experiments were repeated, and this time with unsaturated fat, like omega-6 cooking oils. And they found that these caused even worse sludging of the blood. Just like if somebody cooks with oil, then afterwards when you clean up, it's a real mess and it's difficult to clean up. It can make things all sticky. Okay, let's see what else is interesting. Excuse me. Two researchers, Ray Rosenman and Meyer Friedman, showed that eating omega-6 cooking oils caused the same effect as saturated fat, except it was worse. And they were looking with an 80-fold magnification into the eyes. It was a real cool paper. You see the little small arteries disappearing after the high-fat meal. But there was a confounding variable. There also had high sodium in one of their studies. With the cooking oils, the blood stayed sludge thick for so long, the research assistants wanted to go home. You know, maybe they started the experiment at 8 o'clock in the morning, and now you're going into the night hours, and they still weren't done yet. The average American's eating like two or more high-fat meals per day with oils, and they're keeping their blood thick all day long, so they'll have a tendency to have hypertension, and they're at great risk of progressive worsening atherosclerotic occlusions of the arteries to their heart, their Johnson, and their brains. We talked about this before, how Quo's research showed a 15 to 20% drop in oxygen delivery to the tissues, and Roy Swank and hamster brain noted a 30% drop in oxygen delivery. That's a big drop. Okay. Okay, this is just showing a peripheral blood smear, how almost all the cells are red blood cells. Excuse me, over 99%. If you have a test tube of blood, the red blood cells will sort of sediment to the bottom here with their iron. They're heavy with hematocrit. The little white thing in the middle is called the Buffy coat. That's the white blood cells. And on top of that is the plasma. Typical hematocrit, somewhere around 40 or so. And this is just showing the higher the hematocrit, the thicker the blood will be. The higher the blood viscosity, the more prone it'll be to clotting. Thicker blood pressure goes up. Okay, some of these guys, like these Tour de France bicycle riders, started taking epoetin, and that increases hematocrit, and that would give them more energy when they're in a long marathon distance race on bicycles, but it also meant when they're just laying around relaxing, they had a real high hematocrit. They're more prone to forming clots, and that's thought to be related to the increased number of them dying unexpectedly. Okay, normally the blood plasma is relatively transparent. You can see through the plasma, so to speak, in this typical red blood cell, but a red RBC storage test tube. But when you eat a high-fat meal, it becomes more opaque, the plasma, because there's more fat in there. They had a good picture of that in the movie Game Changers about athletes and how a vegan diet can work well for them. Okay. Elevated triglycerides and elevated free fatty acids in the blood cause insulin resistance. Let's see. Let's see. When you've got injury to the blood-brain barrier, you'll also get increase of the gut barrier. And Roy Swank's research suggested that hypoxia related to high-fat meals were causing, especially saturated fat, were causing injury to the blood-brain barrier. And this increased permeability was thought to be something that can cause brain fog. And in addition, opening up the blood-brain barrier would allow an autoantibody to get access to the brain parenchymal tissue, for example, to cause damage like with multiple sclerosis, thought to be primarily an autoimmune disease. High-fat meals also will cause some distortion of the shape of red blood cells. They can become like acanthocytes with an asymmetric spur. Acantho means thorn, or echinocytes, E for equally spacing of the spurs. Echino's like a hedgehog. That means they're all over the place. So that's all bad. You get decreased flow-mediated dilation, less ability to generate nitric oxide from endothelial cells. Injured blood-brain barrier is associated with leaky gut. So you get all the problems related to that, like postprandial amyloidogenic clotting. It's associated with increased inflammation, and actually also contributes to worsening insulin resistance. Some bacteria are dormant in the blood, and the relevance of dormant bacteria is they can be reactivated if there's elevated blood iron. And if you have elevated blood iron, free iron in the blood, that's bad. Iron's kind of like gas in a stove. You know, it's good when you in the spot where you need it, but it's not good elsewhere. And it can cycle the iron. This is called ferrous redox cycling, back and forth between Fe2 plus and Fe3 plus. And that can activate dormant bacteria. That also can damage tissue by generating free radicals, and that'll increase oxidative stress. Oxidative stress means just means you got more oxidants than antioxidants, and they can damage the tissues. Excessive psychological stress, sleep deprivation, caffeine, they all increase catecholamines and cortisol. They can have a prothrombotic effect. We've talked about that before, like the increased fibrinogen. You'll also get increased factor VIII, antihemophilic factor, and von Willebrand factor, and platelet activation. Okay, high-fat diets associated with obesity, with hypertension, diabetes. Okay, everything bad. All right, let me see, where am I at here? I'll go just a little more. If you ingest a high-fat meal, you'll get the release of myeloperoxidase, that's abbreviated MPO, MP peroxidase, perox, and then peroxidase, oxidase with the O, so that's MPO. So a high-fat meal activates neutrophils, then the neutrophils release MPO, which is highly cationic, meaning very positively charged, into the blood. The MPO binds to red blood cells, can cause their shape change. The MPO also can bind to endothelial cells, and it'll overcome their endothelial cell zeta potential. Okay. They can cause endothelial glycogens to collapse. All right, we're going to end this one here, and then I'll go into more of this endothelial glycocalyx collapsing in response to high-fat meals, causing the neutrophils to release the myeloperoxidase, the MPO, and that'll be this cationic stuff, positively charged stuff, which then causes collapse of the glycocalyx further, and you can get binding of neutrophils, for example, to these receptors.